Hello guys, I am Fahad Iqbal. I welcome you to my channel Comparative Physics. In the previous lecture, I have discussed electric fields and defined the electric field intensity due to a point charge and also for a system of charges. Do you know that it was Michael Faraday who introduced the idea of electric fields in the 19th century? He thought of the space around a charged body as filled with lines of force. These electric lines of force, which we now usually called electric field lines, provide a nice way to visualize patterns in electric fields. So in this lecture, I will discuss electric field lines and its different properties. You must be thinking of what is electric lines of force. So let me define it. An electric lines of force is a path along which a small positive test charge would move if free to do so. Okay? So let me write it. An electric lines of force is the path along which a small positive test charge would move if free to do so. What does this mean? It means electric lines of force is the path on which a test charge. You know that what is the test charge? A test charge is a charge which you have bring to know the electric field intensity of a source charge. So the test charge will move on this electric lines of force if it is free to do so. So let us now try to represent electric field E due to a point charge pictorially. So let us try to represent E due to a point charge pictorially. Suppose a point charge is placed at the origin. Okay. So now draw vectors pointing along the direction of the electric field with their lengths proportional to the strength of the field at each point. So you can draw the vectors, okay, like this. Okay, so as you can see from here, as you are getting away from the charge, the length of the vector is getting smaller. Why? Because you know that the length of this vector actually represents the intensity of the field. As you know that the electric field intensity is inversely proportional to the square of the distance between them. It means as you are getting away from the charge, the field strength is becoming smaller and smaller. Okay, that's why you can see from here, as you are going away, this vectors is getting shorter, and it tells actually this vector contains the information. What kind of information it contains? It contains the information of electric field intensity. Okay, it is telling you that as you are moving away from the charged particle, its intensity is getting smaller and smaller. Okay, you can draw many lines. Okay, the number of lines is not have much more meaning here actually. Okay, actually you can draw infinite number of lines. What is important here is the information it contains, and the information is that it is telling you as you are going away from the charged particle, the intensity of the charge, the intensity of the field of the charge is getting becoming smaller and smaller. As we have just seen that the electric field lines contains the information of electric field intensity. It means there is a relation between electric field intensity E and electric field lines. Let us now see what is this relationship. The density or concentration of electric field lines is a measure of electric field intensity E. The greater the density of electric field lines in a region, the greater is the electric field intensity in that region. And the lesser is the density of electric field lines in a region, the smaller is the electric field intensity in that region. Okay, thus we can say that the electric field intensity, at a point is directly proportional to the number of electric field lines crossing normally a unit area around that point. Okay, suppose a positive point charge in space. Okay, so we are supposing a positive point charge in space. So, and also suppose let the total number of electric lines of force originating from the charge is N. Okay, one thing you should remember here, the total number of lines does not change with distance from the charge. Okay, so what is the electric field E1 at a distance R1 from point charge you can write it as E1 is proportional to N upon 4 pi R1 square. Is that? Four pi R1 square. So where what is 4 pi R square? It is the actually area of a sphere. Four pi R1 square. Also, the electric field E2 at a distance R2 where R2 is greater than R1 from point charge is, how you can write this, is E2 will be proportional to N upon 4 pi R2 square. Okay, so when you divide E2 by E1, what will you get, or E1 by E2? So that on dividing E1 by E2 you will get R2 square by R1 square. You can see N upon 4 pi and N upon 4 pi will cancel out, so this will be R2 square by R1 square. Okay, it means, what does it mean? It means that, again you see here, the electric field intensity is inversely proportional to the square of the distance. Okay, that means the intensity of electric field will be decreasing as you are going away from the charged particle. So you can say that the electric field intensity is greater near the charge and it is smaller as you are going away from the charged particle. Let us now discuss the properties of electric field lines. So what is the first property? The first property is electric field lines starts from positive charge and end at negative charge. Okay, and if there is a single charge, if there is a single charge, they may start or end at infinity. They may start or end at infinity. So if you have positive charge here and you have a negative charge here, then what will happen? It will start from positive charge, end at negative charge, like this. Start from positive, end at negative. Like this, okay? And if you have a single charge, okay, then it will be going to infinity. For positive charge, it is going away, and if there is a negative charge, it will be coming towards the negative charge. So let us now see second property. Okay, it says that electric field lines can be taken to be continuous curves without any break. As you can see, these are continuous curves. Okay, there is no break. So the electric field lines can be taken to be continuous curves without any break. So what is the third property? The third property is electric field lines cannot pass through a conductor. Okay, it says electric field lines cannot pass through a conductor. It means electric field inside a conductor is zero. So you must be thinking of why electric field lines cannot pass through a conductor. You know that conductor conducts because it has free electrons, and all the free electrons lie on the surface. Okay, there is no free electrons inside the conductors. So that's why electric field lines cannot pass through a conductor. Next property is electric field lines never intersect each other. Electric field lines never intersect each other. Okay, why? It means if they intersect, suppose here at point P, then what will happen? At this point you can draw two tangents, okay, one along this and one along this direction. So it means that at point P it has two directions, and you know that it is impossible. Electric field is unidirectional. It starts from positive charge and it ends at negative charges. It cannot have two directions at any point. That's why electric field lines never intersect each other. What is next property? It is property number 5. It is electric field lines do not form closed loops. Electric field lines do not form closed loops. What is the meaning of closed loop? It means if you start from a point and you are coming back to the same point, then only you can form closed loops. But you see, in the case of electric field lines, the electric field lines starts from positive charge and it ends at negative charge. It is not coming back to the positive charge. That's why you can say that electric field lines do not form closed loops. Okay? Well, one more property I want to write here, and that is the direction of electric field E, the direction of electric field E at any point is given by the direction of tangent to the field line at that point. Okay, so it means, as I said here, okay, if suppose this is a field lines, then at any point, if you want to know the direction of electric field intensity at this point P, then you have to draw a tangent at that point. Okay, well, so these are the properties of electric field lines that we have discussed. Let us now draw field lines due to some charge configuration. So first, let us draw field lines for single positive point charge. Single positive point charge. Okay, so as we have drawn earlier also, here if you have a single positive point charge, then you know that the field lines will be going away from the charge. Like this, as you can see. Okay, next I will draw field lines for single negative point charge. As you can see, I have drawn it here. For single negative point charges, the field lines are directed radially inwards. Let us now draw field lines for two equal and opposite point charges. So suppose you have two point charges, one is positive, another is negative. Then for this configuration, you know that the field lines which will start from positive charges and end at negative charges, like this. Like this. Okay, next let us draw two equal point charges. Field lines for two equal point charges. Okay, so suppose if you have two equal positive charges here, one here is also positive charge and here is also positive charge, then how will you draw the field lines? Since these two are positive charges, same charges, they will repel each other, so it will be like this. Okay, it is going away from the charge, but repelling the field of each other. I hope you followed this lecture. If you have any doubt, please mention it in the comment box. I will try to reply you there. And if you have not subscribed my channel yet, please subscribe it to learn more. And like and share my videos so that maximum number of students can get benefited of it. Thank you for watching.